Okay. After all this riveting TV, let's get to business. So today we're gonna talk a little bit more about gauge transformations. I mentioned this in the past, but we saw that there was a gauge degree of freedom when we were talking about the vector potential the first time, the magnetic vector potential, and we showed that if you add something to the vector potential that once you take the curl of it, it disappears, then you're absolutely free to do that. And that is, of course, because the real thing, and remember we talked about the Aronoff-Bohm effect. What constitutes real is sometimes a little bit hard to say, because definitely the vector potential is more than just that thing that you take the curl of and you get the magnetic field. But if you do take the curl of it and you get the same magnetic field, then obviously you're still talking about physically the same thing, because magnetic fields will interact with charges based on what their actual what the actual field is, not what the vector potential is. Again, plus or minus, quantum mechanics. So so we had that degree of freedom, and I said also that the scalar potential has a similar degree of freedom. We can start our line integral for the electrostatic potential. We can start it at any point, depending on sometimes, for instance, we talked about one-dimensional charged objects. Those potentials will have a divergence if you go to r is infinity, because the field goes like 1 over r, and then the potential goes like the log of r. So sometimes you need to put that point of reference somewhere else, but then in the end it doesn't really matter, because in any kind of real situation you bring some kind of a charged object from one place to another. So the point of reference factors out, or doesn't factor out, it just drops out, because it's the same reference for both paths. You can take it out. Now, I mentioned that therefore those two freedoms to pick forms for the potential had implications, so they're not completely free to use. But today we will nail down what that is, and then we'll also be able to change the way that we can describe Maxwell's equations, and we will be able to do this in terms of potentials rather than in terms of the magnetic fields. And it turns out that the equations that you get then are quite elegant, and you'll see that they look for certain gauge decisions, they look very similar for both the scalar and the vector potential. So there's a lot of goodness in there, and that'll help you get to deeper understanding a little bit faster. Then we have we have some other things to talk about, specifically the Poynting vector. There is you've probably seen a lot of this stuff already, but there's a lot of extra formal stuff that we'll have to take care of in order to show that the Poynting vector is indeed that thing that describes how energy can be radiated out of a volume when electric fields and magnetic fields are present, and then there's also charges that are moving. Turns out that actually it's mathematically a little bit of a hairy problem, but at the end you'll get some really nice balance of, you got some kind of an energy that's contained in a volume, and there are two things that can happen with that energy. One is it can radiate out, or two, it can be lost due to the interaction of those fields with moving charges. Those are really your only options. So then the balance that we will find is, well, that thing that radiates out is actually the Poynting vector, and that's the thing that carries the electromagnetic energy out of that volume. And that is the thing that afterwards we will deal with. The potentials working together. So we had worked out that Faraday's law said, Faraday's law said that the the curl of E is minus 1 over C dB dt. Now, we know that, of course, that B is the curl of A. That means we can write this as minus 1 over C ddt as the curl of A. And now I can swap my curl and my ddt, and I can just say this is the curl of ddt of A. And now I'm going to bring everything over to the same side, and then I'll have, go away. Then I'll have the curl of E plus 1 over C dt of the vector potential is equal to 0. Okay. So what does this mean? Well, it means that the electric field together with this vector potential form this vector field that once we take the curl of it, we can expect to get 0. What does that mean? Well, that means that that thing that we take the curl of, this thing here, must be curl free. So therefore it can only be the gradient of a vector field, because that's the only other option. So with a little bit of foresight, we're going to call this thing minus the gradient of some scalar field psi. And if that is the that scalar field, then we know that we can call that psi. We also know that the E field itself already was. E field itself already was minus the gradient of phi. Okay. So therefore, we can write the E field as minus the gradient of phi minus 1 over C dA dt. So now we have taken that that curl of A and pulled it into the potential definition, such that now we have new definition of the electric field as a function of the potentials only, and we no longer need to define it based on what we had before as the time derivative of the magnetic field. Now we have it in terms of potentials only. And then we still have our trusty B is the curl of A. And now we have, therefore, two equations that are both stating E and B in terms of phi and A only. Okay. Now let's talk about gauge freedom. So gauge freedom. What does gauge freedom mean? It means that we can change phi, and we can change A, and as long as we still get the same fields according to these equations that we just wrote down, then everything should be fine. So let's see what that means. So for instance, we could say phi is let's see, let me make that Okay, so let's say we have, oops, we can change phi, and we're gonna say phi is the, a new phi is some kind of an old phi plus some kind of scalar field G. So this phi is our phi prime. And we're going to do simultaneously in one go, we're going to change our vector potential. And we're going to say our vector potential A prime is the original A plus some kind of a vector field G. And the question is, how are those related at all? But we require that E prime is equal to and B prime is equal to the original fields. And the way we check that is by, well, we plug our degree of freedom into our two equations for the fields as a function of potential. Those are our green equations. And we see what we are allowed to do. Okay, so let's start with the blue field first. So we have the E field. We have E prime. So it's by definition should be minus the gradient of our new potential. All right, so because we're doing this in the primed formulation, minus 1 over c d dt a vector prime notation. So we haven't done anything. We just restated our description of the electric field in terms of the potentials, except we have everything in primed form now. So now we're going to change that, and now we're going to write this as this is minus the gradient of phi minus the gradient of G. Actually, let me try to be super consistent in the way that I'm coloring everything. Okay, so then this would be minus the gradient of G. Okay, now we have minus 1 over c ddt of A, and then minus 1 over c d dt of G. Okay, now hopefully you see that these two red terms combined give you the original E field, the unprimed E field. But now we have these two other terms, minus 1 over c d dt of G vector and minus the gradient of G. And we require that the red field is equal to the blue field, so therefore this thing needs to be equal to 0. Okay. So we need to look very carefully at this expression. So let me write this. Let me write this a little bit differently. Is minus 1 over c d dt of G. Okay, so this is the relation that that we need to follow if we are allowed to change both phi and A without changing the actual field. All right. So what does that mean? Well, so we have some kind of a scalar field G. So that's our scalar field G. We take the derivative of it, and then afterwards we get the gradient of a scalar field. Now, there's really no way to get G to look like the gradient of a scalar field if it didn't already look like the gradient of a scalar field to begin with. So we need G to be the gradient of a scalar field, and I'm going to call this thing psi, and that is, by the way, not the psi that I used here, not the same, not necessarily. So we need that extra vector potential to be the gradient of some kind of a psi, such that when we plug that in here, we get a ddt of the gradient of psi, and then now we know that therefore condition number 2 is that g is minus 1 over c ddt of that same psi. So these are the two things that we are allowed to do as long as we're doing this in one go. Now we had two conditions. We require that both the electric field is unchanged and the magnetic field is unchanged. So let's check finally if what the magnetic field is. So the magnetic field B prime would still be the curl of the A prime, which would be the curl of A plus the gradient of psi. And fortunately, the curl of a gradient is 0. So this is the original curl of A, which is our original B. So the fact that we're choosing our G to be the gradient of that scalar field psi is automatically assuming fulfilling that condition. So there we go. So we're allowed to do this, and therefore the transformation that we are allowed to do, so Gage transformations, are that phi is phi minus 1 over c ddt of psi, and our A vector is our A vector plus the gradient of that same, potential psi. So this is what we're allowed to do. These are our Gage transformations that are allowed. So we have a potential formulation now for the electric fields, but we don't yet have Maxwell's equations in terms of potentials. So now to Maxwell's equations with potentials only. All right, here we go. So I'm going to let you work on that for a little bit. I'll write it down. So we have we have two equations that we want to look at first. So we have our Faraday's law, curl of E is 4 pi rho. And we have Ampere's law, which is, or Ampere's Maxwell, sorry, didn't mean to be disrespectful. Ampere Maxwell, it's minus 4 pi over c j, 1 over c ddt of E. I think I am missing a sign here. Yes, my signs are not right. There we go. Okay, so your mission. Oops. Rewrite Faraday's law and Ampere Maxwell in terms of A and phi only, meaning eliminate E and B. Okay, and for completeness sake, so we have our E minus 1 over C ddt of A, and we have our B. These are our curl of A that we'll use.
Dr. Postma?
Yes, sir.
Oh, I'm sorry, I just saw that you were. Okay, for the first one, it's the divergence.
Yes. Okay. So, yeah, after that little thing, see my curls and my divergences. So the procedure afterwards is rather straightforward. It just looks a little messy, so let me just walk you through it a little bit. So, of course, this was supposed to be Gauss's law that we were going over first. And the term here, the E field here, of course, became this term using this expression. And the, of course, the divergence of a gradient is minus the Laplacians. So then that gives you the Laplacian minus, and then there's a 1 over c ddt of the divergence of A is 4 pi rho. Now this is, of course, causality goes this way, right? So the source term is on the right, and it causes that vector and scalar potential on the left. So that's Gauss's law. And then Ampere Maxwell, we're doing the same thing, but of course now we have two things to take care of, because Ampere Maxwell has both the B field, which ends up here then as the curl of A, because that's coming from here, and of course the E field, which goes here. And then the curl of the curl is an identity that we've come across a couple of times already. It's the minus the Laplacian plus the gradient of the divergence. And then we still have those source terms on the right. Just distributing the ddt, we get a second derivative of A dt, and we bring everything over to the left-hand side. And now we still have just that single source term on the right, and we've got this mess of stuff on the left. Now the question is, what are we allowed to do? So we know that we have gauge freedom, but how does that translate to fixing a gauge? What does fixing a gauge mean? Well, remember that what we were saying before, that we're allowed to add something to the vector potential. So the vector potential, I believe I'm mixing my colors. Hang on. So this is our vector potential. And this is, of course, nope. See, now I'm starting to see crosses and dots everywhere. This is by definition. Now, in our transformation, this is our original vector potential plus the gradient of the scalar field that we're adding to it. And that is therefore the divergence of A plus the Laplacian of psi. So in other words, we can make the divergence of A look like anything, because if we're not happy with the way that the divergence looks, we can always add a function to it that is following this behavior, because we are free to do that, and then we can make the divergence look like anything. So that's what you do when you say, I'm fixing a gauge. I'm going to fix a gauge, and I'm going to say, I'm going to pick the divergence of A to be something. And as long as you're As long as you're careful, then you're allowed to do that. Now there's a that is called fixing the gauge. And for instance, there's a Coulomb gauge. Which is 0. Now, the question is, would that actually help us here? So we have two equations that we would like to look at and try to see if we can simplify a little bit. We have this one here, and we have this one here. Now, the top one would work. We can say that that would be simplified if we pick the divergence of A being 0, except then in the bottom equation we would still have the scalar potential here, so that wouldn't work. So what we're going to do instead is we're going to pick a condition that's going to help us formulate the second term exclusively in terms of the vector potential, and you can kind of see already what's required in order to do that. So let me circle the terms that we're going to look at. So we have the I think it's time for a new color. Yes. All right. So we have these terms that we would like to vanish, and you see that we're allowed to do something there, because it's the gradient of the divergence of A, and we also have the gradient of that scalar potential phi, and we're allowed to change both. So we can say, okay, if we pick the condition that this is equal to 0, or stated in terms of the divergence is minus 1 over c ddt of phi, and this is known as the Lawrence gauge. By the way, there is no t here. It's not the same guy as the guy from the Lorentz transformation. Books have been written about how this guy has been slighted, but yeah, it's a different person, Lawrence Gage. Then you'll see a beautiful thing happen. You'll see that in Ampere Maxwell, these two terms disappear, and we get an equation that is only a function of the vector potential. And in Gauss's law, we'll see that we'll get the divergence of A, which is now an extra time derivative of phi. So we'll just get a second order derivative of phi. And then you'll see this really nice thing happening. So then we have Gauss's law that became the Laplacian of phi minus 1 over c squared. Remember, I said that you'll get a second derivative of phi is 4 pi rho. And then Ampere Maxwell looks very similar now, because I again get a Laplacian. Laplacian 1 over c squared dt squared is minus 4 pi over Cj. All right, so two things happen. We have a, I fixed some signs here. We have two formulations for Gauss's law and for Ampere-Maxwell that are basically identical, and they're only a function of phi and of A. So we're going to introduce a new differential operator. Introducing the D'Alembertian. It's this symbol, and it's the Laplacian minus 1 over c squared d squared dt squared. So if you do that, then with the definition of the D'Alembertian, this becomes the D'Alembertian of phi, and this becomes the D'Alembertian of A. And now we have something that looks even smaller. And now we can see this looks a little bit like the like Poisson's equations before, right? So we had the D'Alembertian, which now also includes time dependence, but it's a modification of the Poisson equation, right? Because we have a Laplacian here. So the D'Alembertian here now plays the role as the Laplacian that we had before, except it is, of course, also including the time dependence. And now it also works for the vector potential. So now we have something that looks like Poisson's equation, but we have it with a slightly different differential operator, which is a generalization of the Laplacian, and it works for both the vector and the scalar potential. So we can actually put these two together, and we can write it like this. So we can write this, the D'Alembertian of this funky system is 4 pi rho, and then 4 pi over Cj. And later on, we will see, therefore, that we can write this as the D'Alembertian of some vector field is, a 4 vector J nu, where this 4 potential is the combination of the scalar potential and the vector potential. And this 4 vector is the combination of the scalar potential, scalar charge density and the current density. And that is when we will get to relativity. But you'll see that the more we mess around with these, the more these things start to look like each other. And I hope you are excited about the fact that we'll be able to ultimately be able to say Maxwell's equations are just in this tiny little box, and that's all we need. All right, let's talk about energy density and energy flow. Okay, so let's say that we have some energy density and flow. So let's say that we have some kind of a boundary, some kind of a volume, and in this volume we've got a whole bunch of stuff happening. There's currents, there are charges, Q's, there's E fields, and there's B fields. And inside of this volume, we can talk about how much energy is stored. And then we can also say, okay, what happens if some of that energy leaks out of this volume? How can that disappear? So for instance, could go out this way. All right, so the first thing we need to do is we need to describe what we what we mean by total energy. So the total energy stored in that volume is U. It's the combination of those two volume integrals that we had previously worked out and then integrated over all of that volume. So we know that that's what we have for the total energy. Now we have now relations, quite a few of them, by the way. We have now things that will allow us to describe the E's and the B's in a different manner. So let's look at the following identity, because then our life's going to get a little easier. Hang on, let me do this in blue. So let's say we have a 1/2c ddt of E squared plus B squared. All right. We can write that as a 1/c E, and then due to the product rule, we will get a dEdt on the first E and then on the second E, and those terms are identical. So they double up, and that's why we lost our 2. And we will get the same thing here. We will get a B dotted with a dB dt. Now we know from our Maxwell's equations that our dEdt shows up in ampere Maxwell. So we're going to put that in here. Our dEdt is going to go in here. Let me make sure. Use a nice little box here. So our dEdt is going to be equal to, let me see, where am I? Yeah. Curl of B minus 4 pi over C J. And now that's still dotted with E. And the second term is easier because the dBdt is just a curl of E, but then with a minus sign, right? Because that's Faraday's law. So so that goes here. Curl of E, and that comes from here. And then this becomes a minus sign. All right, so now we have rewritten this a little bit. So we no longer have, even though we started with a time derivative of the energy density, that's exactly what we're trying to get to, right? Because we have that term of E squared plus B squared, and we're taking a time derivative. But now we no longer have it explicitly in terms of a time derivative, but we actually have it in terms of fields and sources. So now, so there's this really neat trick that this is like footnote number 2. So there's a neat little trick that I have to show you. So let's say I want to know what this thing looks like. So I'm trying to do something that looks like the product rule, just like what we were doing above, where we were taking the ddt of E squared, and we got an E dEdt, and then we got an dEdt dotted with an E, and we got that twice. We would like to do something similar here twice, except the cross product's kind of messing with our style. So there's a trick that I believe Feynman introduced. So he did the following. He said, okay, I'm going to call this thing a different operator. and let me, since I have all these colors at my disposal. So I'm going to call this thing a different operator. And really what this thing means is that this is actually not an operator anymore, but now it holds the result. Result of nabla acting on the B part. So if we do that, then we get a term here. So we get our B crossed with E. And then we do the same thing with our with the second one. So we get a E dotted with B crossed with E. All right. Oh, hang on a second. Yes. Okay. Now the first term is now, because it's not an operator anymore, we're just assuming it's just kind of some kind of a vector field that just holds the result of that that operation. Now I could just treat it like a vector field, and I can start moving it around as if it's not an operator anymore. And because it's only acting on B, as long as at the end of the day I get something that has the operator on the left-hand side of the B field on the right, then everything should be clear. So I can basically move our quantities like this, and I'll get an E dotted with that weird operator crossed with B. Okay, now I can do the same thing here on the right, but here I need to change the change not only the order, but change permute the vector fields, but I also need to change the orders, right? Because if I bring the nabla over to here, then I have the nabla operator working on the B field, and I don't want that. So I need to go twice, and then I also need to change the order. So I will end up with a minus. With a minus B dotted with, and now I have this thing here, the gradient of E. Okay, now we have it actually in regular form again, because now our operators are actually, if we assume that the operators are working on the right only, which is how we traditionally have operators working, then this is actually in the regular form again, which means that our where's my curl of B? Hang on a second. Curl of B, curl of B.
In the yellow?
Yeah, here we go, yes. So what I'm doing now, so I have my E dotted with my curl of B, which I have there, and I also have here. And now I have my B dotted with the curl of E, which I also have here, and I have the right sign. So now, meanwhile, back at the point, we get to do the following. We have a 1 over C, and we have an E dotted with minus 4 pi over Cj. Yes. And then finally, we have minus the divergence of E crossed with B. All right. So now we have reworked this time derivative of the E squared plus B squared in this form. So now if we go back to our original energy density, then we say that ddt of U is going to be ddt of the 1 over 8 pi E squared plus B squared, da, 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 da. We throw in all the factors of C that we need, and we end up with the following two terms. We get a minus, and we have a J dotted with E, and that is integrated over the volume still, of course. And now a second integral, and that is our E over B. And I need a 4 pi, hang on a second. Four pi C D3X. All right. So the divergence, oops. Yeah, divergence came from there. Okay. So now we have a time derivative of the electric field, sorry, of the energy. And this thing we're going to call S, and it's the Poynting vector. This J dot E we need to talk about a little bit. I'll show you two ways to think about this. So so if you use Ohm's law, in differential form, oops. Which is J is sigma E. So not R is V over I, but they're both the same. Then this first term here is actually saying it's sigma E squared. And sigma E squared is energy loss per unit time per unit volume. So that is, so sigma E squared is energy loss per unit time and per unit volume. So what does that mean? Well, that means that once we integrate that over the volume, that means that that electric field, together with that current, however they come about, if there are ohmic losses, you know, there's resistors in there, or a resistive medium, then finally, when we integrate that, we will have the energy loss. So now we have a balance of a couple of things. We have a ddt of U, we have minus the energy loss, total energy loss integrated over time, and we have minus this integral of the divergence of of this new Poynting vector S integrated over volume, but using using Gauss, we can change this into a surface integral. So I'm going to change this. Oops. I'm going to make this into S d A vector. And now we have a very nice balance of a balance of energies. We have now in our volume, what did I have here? Here we go. We have our volume, and we have energy flowing out. So that is this term. So this is our energy flowing out or in, could be anything. So that's our energy flowing out. Then we have the total energy stored here, that's U. And we also have losses because there's maybe stuff happening here. And these are our E losses, and these are balanced. So you have a certain amount of energy stored in this volume, and the only way it can decrease is if we have losses, so the black term, or if we have an outflow of energy through the red term, which is our Poynting vector. And if you want, you can also write this in a local form. So in local form, where you have a ddt of little u, so that's now energy density, is a minus J dotted with E minus the divergence of S. So the let me actually use my same color schemes. Give me a second. So we have a ddt of the energy density, that's now little u, and then we have an outflow of the energy, of the energy through the Poynting vector, and these are balanced. And that's energy density. These are losses, and this is outflow, or if you want to think about it in inflow, it depends on the sign of S. So compare this to charge conservation. So look at the charge conservation formulation in local form. We have a ddt of rho, so charge density is equal to minus the divergence of J. So they are in formulation very similar. So we have some kind of a time derivative. We have some kind of a divergence, which is capturing that there's stuff that's flowing out, except now we have this extra term, which is also capturing the losses. There's another way to look at these losses, and not using Ohm's law, but for instance, you can write explicitly another way to analyze the losses. It's a little bit more general. So for instance, we are looking at a term that looks like, so it's this J dot E. Now let's say J is due to some kind of a set of charges A, QA, that are moving with velocity A, and they're at some position R minus RA, and we dot that with E. Then the thing we will end up with is products of this form. So V dot E with a Q. Now that is just a V dotted with a QE, which using Lawrence force law, you can write as the force, which is going to cause the momentum to change. So that's going to be dP dt minus the Q V over C crossed with B. Now the beautiful thing here is that this V and this term, these are going to cancel because they're perpendicular to each other. So this is going to be V dotted with dp dt, which is actually ddt of p squared over 2m. So that's your kinetic energy. So putting this all back together, also in this manner, this term j dot e is going to show you that your energy is being lost. Okay, so that's the general picture. So we have energy in this volume. It's stored in the electric field and the magnetic field. The electric and magnetic field can interact with the currents and with the charges, and in fact, the currents and the charges themselves could be the source of those electric fields and magnetic fields. But in the end, when all is said and done, when there's losses, that's going to come at the expense of the energy that's stored in that field, or some of that energy might actually flow out of the volume through the Poynting vector, which expresses the way that the energy flows. So the Poynting vector is going to be that thing that we will need. Poynting vector is our entry into electromagnetic waves. And that's the thing that'll carry the energy, and that'll actually be the wave, because wave is not necessarily an electric field or a magnetic field. It is both the electric and the magnetic fields simultaneously. Okay, all right. Well, ladies and gentlemen, through this heroic effort, we were able to describe Maxwell's equations in terms of potentials only. We figured out how to get rid of our gauge degree of freedom, and we found this thing that seems to unify the electric scalar potential and the magnetic vector potential into something that looks like a wave equation for both the electric and the magnetic field components, where the vector potential only talks to the current density, which makes sense because that's kind of how we think about magnetism. And the scalar potential, which is like electrostatics, only talks to the charge. And all the time dependencies are taken care of because we chose the right gauge. I hope you appreciate that. That's a very elegant point of view. Now, gauges are a whole thing when you start doing field theory. If any of you ever gets to it, at some point you need to let go of your gauge freedom, and then it becomes a really different kind of subject. So don't take it for granted. Just the fact that we can do it now is it's a nice thing. Doesn't unfortunately always work as well. So with that, that's all I had for today. Any questions? Hang around for office hours, and I'll see you all on Wednesday.